Good afternoon, everyone. I'm Cheng Li. Today, I will present our recent work of how to make the trade-offs between latency and consistency in geo-replicated systems. It's a joint work with my colleagues, Daniel Porto, Alan Clement from Max Planck Institute for Software Systems, Johannes Gerke from Cornell University, Nuno Preguiça, and my advisor, Rodrigo Rodriguez, from the Nova University of Lisbon. The goal of our work is to improve the user-observed latency while maintaining consistency semantics. So, why does latency matter? To answer this question, let me show you some very interesting results from the experiment conducted by engineers at Microsoft Bing. They artificially injected delay before sending responses back to their users, and what they found there is, as the latency goes up and the revenue per user significantly goes down. Given the importance of low latency access, which is stressed by this graph, online services, they normally replicate and distribute their state across multiple data centers, as you saw in last presentation. And then they direct the user requests to the closest data center to avoid intercontinental communication overhead. Nowadays, such a solution is adopted by major providers of internet services. Just as you saw, Google used this solution. In addition to that, Amazon and Facebook do so. However, replication doesn't come for free. Once we replicate the state across multiple sites, we must ensure that all the replica to be consistent. Some solutions, they adopt a strong consistent model. They will guarantee that the system is always consistent, and it provides natural semantics. However, it incurs high latency. On the other hand, some solutions, like Dynamo Bio, they adopt eventual consistency, which they allow operations to be optimistically executed at the local site and lazily replicated across multiple sites. Therefore, this kind of solution provides you low latency, but it may introduce some undesirable behaviors, such as the last seat on a flight may be given to two distinct users. The question here, can we bring these two different consistent models together such that we could build a geo-replicated system in both the consistent and fast fashion? The answer to this question is, yes, we can. In this talk, I will going to talk about how actually we build a system to support the coexistence of strong and eventual consistency. And then I will detail how actually we can modify applications to, on the one hand, to be fast and use the eventual consistency whenever possible, while without sacrificing consistency semantics. At the end, I will show you the experimental results. The key of making system fast is to find the balance between strong consistency and eventual consistency. As you know, strong consistency totally order operations. Here is one such example of the total order. Arrows between operations indicate their ordering. When two operations are ordered, we say one operation depends on the other. This means that these two operations are executed in that sequence, and the one operation saw the effects of the other. Different from the strong consistent model, eventual consistent model partially orders operation, which means operation may or may not depend on each other. Here is the one example of such partial order. Unlike this two consistent model, our work allows the operations to be associated with different consistent levels. To achieve this, we first label strongly consistent operations as red and the eventual consistent operations as blue. And then we combine these two different consistent levels together, and this combination results in a new consistent model, which we call red-blue consistency. It's very important to note that all the operations are still partially ordered, but additionally, all the red operations must be totally ordered with respect to each other. Our goal with this model is to provide low latency by running operations with eventual consistent semantics as much as possible, and only coordinate operations for strong consistent semantics when needed. In order to achieve this, we must instantiate this model into a system. Therefore, we built our system, which we called Gemini. Gemini system is the coordination and the replication layer that supports red-blue consistency and replicate blue-red operations across multiple sites. Here, this graph shows Gemini system with the two-side configuration. We have two users, Alice and Bob. They're interacting with different sites. So currently, Alice wants to issue a blue operation A1. The local site can always accept the blue operation without any communication with the remote site. Therefore, A1 will be accepted in a global partial order, and then it will be executed locally and also replicate at the remote site. Simultaneously, at Bob's site, Bob issued another blue operation B1. The same story of A1 is applied to B1. Subsequently, at Bob's site, B2 comes into the system. It established a dependency with B1. Meanwhile, at Alice's site, she wants to issue a red operation R1. The processing of the red operation R1 is more complicated because we must serialize all the red operations. To do so, we regulate at each point a red operation can be accepted if the corresponding local site holds the red flag. So here, R1 is very lucky because the red flag is at the corresponding local site. Therefore, similar to the blue operation, R1 will be executed locally and pushed to remote site. At some point, at Bob's site, Bob issued another red operation R2. At this point, this R2 cannot be accepted since the red flag is not in the Bob site. At some later point, the remote operation and the red flag arrived at the Bob site. Now, the local coordinator can accept R2 in this global partial order, where R2 not only depends on its local operations, but also the remote operations, namely A1 and R1. For the remaining operations, our Gemini system processes them using the same solution. And all the operations are either executed or replicated at both sides. At the end, we got the partial order and two execution orders. There is a very important point to take away from this example. This global partial order defines a set of the dependencies among operations. And operations can be executed into different sequence at two sides, provided both sequential orders must be compatible with the partial order. The importance of these two different execution orders is that they allow us to make a system fast by running blue operations locally. And this flexibility also introduced a challenge. The challenge is that we have to ensure that the replicas of two sides converge. I already talked about the red-blue consistent model. Next, let's apply this consistent model to a simple bank system and explore how this model works in practice. This is a very simple bank system with only three operations, namely deposit, accrue interest, and withdraw. Initially, we want to make the system as fast as possible. Therefore, we label all the operations as blue, which means these operations can be executed independently without knowing each other at the different sites. Suppose now we have two users, Alice and Bob. They're sitting at a different site, but they share the single bank account. Initially, this bank account has $100, and currently the interest rate is 5%. Simultaneously, Alice wants to deposit $20, and Bob wants to accrue interest. After these two operations take place, they will be propagated to the remote side, and then these two operations will be incorporated in respective local histories at the two sites. At the end, Alice observes she has $126, but at Bob's side, he decided observe a different value, which is 125. In this example, we found a problem. The problem is that we introduced a divergent state. The root cause of this problem is accrued interest doesn't commute with deposit, but these two operations are executed in two different orders at two sites. Initially, we want to get the fast responses, and we label all the operations as blue. But now, in order to get the state convergence, we have to label all the operations as red. And the consequence of this labeling is a huge performance penalty. This bank system example indicates that the challenge of making system fast is to label more operations as blue. Before addressing this problem, so let's recap where we are. I already introduced the red-blue consistent model and its underlying Gemini system, and also showed you a bank system where all operations must be red. Next, I'll tell you how we can transform this bank system to make more use of the blue and the faster operations and at the safe side. What prevents us from running this bank system as fast as possible is the way how we actually replicate the operations. In the previous example, we replicate operations directly across multiple sites. The problem of this replication is that the two executions of the same operation may apply different changes to the system. Take the accrued interest as example. When accrued interest was first executed at Bob's site, it decided to add $5 to the bank balance. However, when it was applied at Alice's site, it decided to add a different value, which is $6. The easiest way to solve the state divergence problem is to force these two executions to apply the same change. To do so, we split the execution of accrued interest into two parts, namely a generator operation and the shed operation. Both operations are mapped to two different execution phases. The generator operation corresponds to decide phase, where it identifies what kind of change the original execution wants to make, and it itself doesn't have any side effects. And the shed operation refers to the apply phase, where it actually makes this change visible. With this separation, our replication scheme works as follows. Users issue operations to its corresponding local site, and then the local coordinator will invoke the generator operations. The generator operations will make the decision based on its current local state. And when this generator operation finishes, it will produce a shed operation, which will be encoded the decision and the state when this decision was made. It's very important to note that we will not label the original operations. Instead, we label the shed operations. So the shed operation will be either red or blue. At the end, the shed operations will replicate at both sides, and the change introduced by the shed operations will be independent of the local state. By following these ideas, we introduce the generator operation and the shed operations to the bank system. Each generator operation look very similar to their original operations. The only difference is that the generator operation will produce a shed operation at the end of each execution pass. For example, the generator operation of deposit, it will identify how much money the user wants to add, and then it will produce the corresponding shed operation deposit prime, which will apply the certain amount of money to the balance. More interestingly, the generator operation of accrued interest, it will compute the delta based on its local state, the balance, and the interest rate. And then it will encode the delta into the shed operation accrued interest prime and ask it to apply the delta to the balance. For the withdrawal, it has two different execution paths, which led to two different side effects. Therefore, we introduce two different shed operations to this example, namely withdraw ACK prime and withdraw fail prime. The withdraw ACK prime corresponds to the successful withdrawal where it decreases the balance by a certain amount of money. And the withdraw fail prime corresponds to the failure withdrawal, which doesn't have any side effects. It's easy to say that these four shed operations, they commute with each other. Therefore, we can label them as blue. And in the following examples, I will show you how these four shed operations help us solve this state divergence problem. For simplicity, I will use the shorthands instead of full names. Let's start with exactly the same example with the same set of the operations and the state. So currently, Alice and Bob, instead of executing the original operations, they will first invoke the generator operations. And the corresponding shadow operations will be produced at the end of each generator operation. And then the shadow operations will be first applied locally and then replicate at the remote side. At the end, we observe the convergent state, which is $125. Problem solved. And here, we already know that accrued interest and deposit, they work properly, but it is not the case for withdrawal. So next, let's say what will happen if both of them want to withdraw a certain amount of money. For example, Alice wants to withdraw $100 and Bob wants to withdraw $80. Again, the corresponding shared operations will be first applied locally and also remotely as well. At the end, we observe the convergent state, which is good, but this convergent state is minus 55. This minus number indicates that we found another problem in this example. The problem is that the two sides observe a negative state balance, which means we broke a fundamental invariant in this bank system, which says that the bank balance must be always non-negative. The cause of this problem is that the successful withdrawal shared operation potentially break the invariance, but we didn't coordinate them. To prevent this, we have to label this successful withdrawal shared operation as red. From these examples, we already know how to label operations to make this system work properly in this particular case. Next, I want to generalize these ideas into a labeling methodology. This labeling methodology will guide the developers to decide which operation must be red and which operations can be blue. This classification scheme is quite straightforward. For each shared operation, we first check whether it commutes with all the other shared operations or not. If it doesn't, we must label it as red. This labeling ensures state convergence. Otherwise, we continue to check whether this shared operation potentially breaks invariance or not. If it does, we must label it as blue, as red as well. This labeling is ensuring the invariant preservation. For the remaining uncolored operations, we can safely label them blue. To summarize here, in the first part of my talk, I introduced the red-blue consistent model, which supports the operations are either eventually consistent or strongly consistent. And second, in order to get more blue fast operations, we split operations into generator and shared operation pairs. And the last point I made is that we teach the developers to classify operations. We formally proved that the labeling methodology we proposed leads to state convergence and the invariant preservation. In the second part of my talk, I will present how actually we modify the applications to use the red-blue consistent model and the experimental result. The evaluation part mainly focuses on three questions. The first one is how common are blue operations in existing applications? The second question is, are these blue operations enough to make the system fast? The last question we want to understand is whether red-blue consistent model allows us to process more operations. To answer this first question, we selected three applications, namely TPCW, Rubies, and Quaddy. TPCW is an online shopping cart benchmark. Rubies is online auction benchmark. And Quaddy is a social network application. The first task we did was to analyze their source code and manually apply the labeling methodology to the original operations. Read-only operations are always blue since they're trivially commutative and they don't break any invariance. Therefore, here we only focus on update operations. Initially, we have to label all the original update operations as red. The reason is that they don't commute with each other. Therefore, the second task we did was to write and design and classify shared operations to the original update operations. And the final result is summarized in the last column of this table. What we found there is using the concept of generator and shared operations, we extended the scope of blue operations. Namely, we found many operations are blue and few operations are red. However, these results are static numbers. More interestingly or importantly, we would like to know the runtime decision of choosing red or blue shadow operations. Therefore, we run different applications with different workloads, and we measure the runtime blue-red ratio. And the result is summarized in this table. What we found there is, originally, before we introduced the shadow operations, each workload demonstrates a significant amount of red operations. However, after we introducing the shadow operations, we dramatically reduce the number of the red operations, and at the end, we end up with the fact that the vast majority of the operations are blue. Intuitively, the high prevalence of blue operations does allow us to make the system fast. However, we don't know how fast the application can be when they run with our system Gemini. Therefore, we further explored the impact of the red-blue consistency on both user-observed latency and throughput. We run these 3 applications with Gemini system. We deploy the system across 5 sites in Amazon EC2 platform. And we put the users at all the 5 locations, and the users are always connected to the nearby data center. And here I only covered the partial result of TPCW. The result of the rubies and quality, they look similar to TPCWs. For details, please refer to our paper. The first set of results I want to show you is the overall average latency for users at all the 5 sites. We first replicated original TPCW in a single site, which is the east coast of the United States. And we connect all users to the single site. And then we replicate red-blue consistent TPCW with Gemini system across 5 sites. And then we compare the result against the one-site setup. What we found there is, in the one-site setup, all the remote users, they observed very high latency. That is because the runtime latency for them to reach the data center in a wide area network. However, our 5-site setup allows make all the users observe the uniformly low latency. That is because, in this case, all the blue operations always getting fast responses. Our solution not only improved the user observed latency, but also improved the throughput. Therefore, we take a look what's the impact of the red-blue consistency on throughput. Here is the peak throughput graph of different deployments of TPCW shopping mix workload. Again, we replicate original TPCW in a single site, and then we replicate modified TPCW with our system across multiple sites. What we observe there is, in a single site, our system is slightly slower than the original TPCW. But once we move to the multi-site scenario, our system outperforms the original TPCW, and we found that the peak throughput keeps being improved as we add more sites to replicate state. The reason for that is read-only operations are never propagated, and the replication of the shadow operations are cheaper than the execution of the generator and the shadow operations together. In this talk, I hope I convinced you that for both the performance benefits and the consistent semantics, we must allow the strong consistency and eventual consistency to coexist in a single system. Red-blue consistency is such a solution to achieve this. The split of generator and shadow operation allow us to make more use of the faster operations. Third, the labeling methodology helps us prevent the state from diverging and the events from being violated. At the end, I show the experimental result, which indicates that our solution improved the performance of the system in terms of both latency and the throughput. Thank you very much. I'm happy to take any question now.
Yang Tang from Columbia. So can you automatically generate the generator operations and the shadow operations from the original ones? Or do you have to let the application developer write the new operations?
Okay. So it's a very good question. So far, we actually in this work we manually check these applications and manually design the shared operation to the original operations. We leave this automation as future work. Thank you.
Okay, thank you.
Nicolas Schipper, Cornell University. You may have answered the question already, so I apologize if that's the case. But so I was wondering if identifying this generator operation and shadow operations help you to figure out which operations can commute and which can't. Because I imagine that for certain applications that might be difficult to do it manually.
Okay. So far we for the both the generating the shared operation and also classification, we provide these general rules which I already described in the talk. Actually, it's check the commutativity and then we further check the invariance preservation. So far we manually do that. So and from our experience in this when we work with these three applications, we found that this work is not very difficult. We spent like one week and to be familiar with the code base and to do this stuff. But we believe that the automated tool also help the developers make the decision. Therefore, we're looking at this. Thanks for asking.
Thanks.
Yeah.
Hi, Mike Friedman, Princeton. If I understood it correctly, locally you preserve partial ordering, right? So you can't actually move a blue operation before another red operation. Is that correct?
Yes, because we preserve the causality,
yeah, okay.
Which means
So my question is, so it looks like the red and the blue actually you have a bimodal performance that red actually has to wait for that flag to push it over. So if you're waiting for a wide area latency and a red operation, let's say, costs 100 times slower than a blue operation, you actually do head-of-line blocking behind that red operation. So it's actually not clear to me that even if your ratio is 100 to 1, why your latency actually isn't just dominated by the red operation and you just basically queue up the blue operations and you don't actually improve performance.
Sorry, can you repeat the question again?
So if you can't reorder blue around red,
yeah, exactly.
You have to wait till red completes. And let's say red is 100 times slower than blue. So even if you have like a 100 to 1 ratio, you're still basically going to queue up behind reds.
So the red operation and blue operation, they can happen concurrently if they don't have the dependencies, right? So once the user...
Interest then deposit. You have to wait till interest finishes before you
deposit. The blue operation don't need to wait. In the case if it doesn't observe the effects introduced by red operations, right? So probably we can discuss offline. I will give you the detailed explanation for that.
Okay, thank you.
Thanks. Yeah.
Marcos Aguilera, Microsoft Research, Silicon Valley. You may want to take a look at the work by Pedone and Schipper on generic broadcast, but basically there's no fundamental reason why you just want to have two callers, and what their work have done about 10 years ago was to define a conflict relation where for every pair of operations you specify whether those operations conflict with each other or not, and they have protocols that ensure that several of the replicas will receive messages in the order that would respect the conflict relation. So that's related work that you may want to take a look at. And of course, generalized boxes by Leslie Lamport is also even more general than that.
Okay, thank you.
Thanks. Don't get up. We have an important message.
My daughter. So you guys may be aware of this Asian Pacific Workshop on Systems, or APCs. This is an initiative of the international system community aimed at building the system community in the Asian Pacific area. It's strongly supported by a bunch of people that most of us know. For example, if you look at the steering committee, we have Gernot, we have Peter Drusho, we have Franz. And also, most of us probably also know the past PC chairs as well. For example, in the last APCs 12, it was chaired by Satya from CMU. It was in Seoul, well attended with around 50 submissions. So the next APCs, APC 13, will be in this exotic Taipei, Taiwan. And we're still trying to figure out the dates, but most likely the submission deadline will be in June, and the workshop date will be in September. And Jane Liu from Academia Sinica, Taiwan, and I will be co-chairing this workshop. We basically take a really broad view of computer systems and welcome papers on broad system topics such as operating systems, cloud, reliability, security, virtualization, basically you name it. So please consider submitting to APCs next year.